Good afternoon, everybody. I hope everybody's staying safe, staying healthy, and staying at home. Unlike myself, I'm here in the classroom again, as you can see, and we're going to keep it moving. So we're going to go into Unit 92. This is for my 170, my advanced students. This is the good stuff. This is the troubleshooting module or the troubleshooting chapters. And I feel like a lot of y'all are well prepared already a lot of the stuff that we'll cover, I think y'all are already doing plenty of. So pat yourselves on the back for that. You guys can pretty much troubleshoot a residential system, and you can apply those same techniques to the larger commercial and industrial stuff. It's just a matter of getting familiar with the new equipment, seeing what's what, and then once you do that, you'll be like, oh, okay, it's the same as the other stuff. And then you just take it from there and start the process of elimination. So anyway, let's get into it. So we are on chapter 92, troubleshooting. So the objectives are discuss common questions customers ask service technicians, outline the basic phases of troubleshooting, outline an electrical troubleshooting procedure that uses the process of elimination. Discuss the use of common refrigeration system performance indicators in troubleshooting refrigeration problems. Explain how to use manufacturer provided troubleshooting aids. Troubleshooting, the process of identifying problems, determining their cause, and correcting the cause of the problem. That's what we do. Effective troubleshooting requires problem solving. The technician needs to do more than just try to match symptoms with causes, as most symptoms have many possible causes. 6 crucial questions. These are questions that customers ask. Some of the questions get real stupid, so try not to make customers feel bad. I mean, they don't know. But these are some of the more common ones. How is the equipment supposed to operate? Oh, actually, no, these are questions that you probably want to ask yourself. How is the equipment supposed to operate? What is the equipment? What is the equipment doing wrong? What is the cause of the problem? What tests are performed to determine the cause of the problem? How can this be corrected? How much will this cost? So these are questions from the customer, but you kind of asking yourself these questions as soon as you arrive, like, okay, what can it be? Once you start listening to the customer talk, you'll start drawing certain conclusions already. Of course, let them finish and see if you can get to the root of the problem. So being able to explain how equipment is supposed to operate makes explaining what is wrong easier. Technicians should be able to clearly explain what is correct about the operation of the unit. If possible, explain why a component or situation is causing the problem. Explain the specific test done. Also, be prepared to offer solutions. Record all tests as this information is generally used to calculate cost. System approach to troubleshooting. All system components depend on each other. Electrical, refrigeration, airflow, combustion. We talk about that all the time. If one thing is not right, it's going to affect the other things. So whenever you're addressing one problem, you're kind of doing a full-on inspection. Excuse me. Excuse me. You're doing pretty much a full-on inspection of the entire unit. One second. Not a cough, just clearing the throat. I do not have corona. So, where are we at? It is difficult to examine one aspect of a system and ignore the rest. Technicians should understand the interrelationship between different system components. Be aware of the effect one process has on the rest of the system. That's very important. Stuff like a dirty filter can affect your refrigerant pressures. It's hard to understand to the rookies, but I feel like all of y'all apprentices, at least the ones that I've dealt with, are a little bit more than a rookie. I rather use the word apprentice, like a seasoned apprentice. So stages of troubleshooting: system operational sequence, preliminary system inspection, collect operational data, what is operating incorrectly, test to isolate cause, corrective action. So that's basically the process. You always want to start at square one, which is the thermostat. Always turn it on from the thermostat, see what the system does, and we'll let it go through the sequence of operations. And knowing the sequence will help you pinpoint what the issue is, because once the issue rears its head at that particular point in the sequence, you can rule out everything before it because all that stuff worked. And the stuff after it, you can check later because we haven't even got to it because we stopped at whatever point we stopped at. So that kind of helps you by knowing the operational sequence. Preliminary inspection, obviously you want to just make sure things work right. Even visual inspections, make sure you don't have obvious wires disconnected or switches off, simple stuff like that. Furnace is not plugged up. And then once you start running it, do your start collecting your data, check your temperatures and pressures and things like that, amp draws, and those things will tell you right away if you have an issue. What is operating correctly, you can rule those things out, and then isolate the cause. So when you do find an issue, you want to isolate that issue, or whether it's the electrical or mechanical, and then and attack it and go ahead and make the repair. Understanding the system operational sequence. Understand how a machine is supposed to operate before arriving at the job. How's it going, sir? 10 minutes. Okay. All right. So, sources of information: manufacturers, installation and operation manuals, unit wiring diagrams, unit charging charts. We've gone over a few charging charts in the in the lab, so we all seen how we find the target subcool. So you'll see things like that on various units. Obviously the wiring diagrams, we've all been real familiar with those. So those are your tools to help you figure things out. The most common way I use the wiring diagrams are to trace out what's in front of me and compare to the diagram and make sure that things were done right. If not, I'll go ahead and make the correction. Sometimes things will be altered, but not necessarily in a bad way. Some accessories may have been added after the initial install or what have you. So when you do see something that's different, just kind of trace it out and see what it's there for. Understanding the system operational sequence. General textbooks, equipment panels, manufacturers' websites, find the latest service bulletins and updates here. So staying updated on the equipment is always a good thing. But one of the tools that I don't see mentioned here or hardly ever is tech support. That's your ace in the hole. You call them before you call the office and admit failure. Always, always, always. I would even ignore my boss's calls at times until I can get a hold of tech support so I can get some better answers before talking to the boss. So that would be your ace in the hole. Obviously, you want to check as thoroughly as possible before calling them because, like we've talked about, they're going to ask you questions. They're going to ask you, did you check this? Did you check that? So it's always nice to be able to say, yes, and it was this. I checked that and I got this. Help them help you. So typical operating sequence. So here's a chart, air conditioning operation sequence. So this kind of breaks down how this particular unit works, which is basically the typical operation. So what does it say here? So technicians should have an understanding of the basic sequence of operation for most types of systems. Charts are read from the top down. Items and columns occur in sequence. Events are in bold. Details follow. So let's go ahead and start at the top. So we have air conditioning operation sequence, thermostat terminal R, control power. R must be, this is really small. I got to get all up on here. R must receive 24 volts for unit to work. So that we know. Everybody should know that. Anybody who don't know that, you know it now. But if I could see anybody's face right now and they were confused, it'd be push-up time. Because now we all know this. So R needs to be energized in order for anything to work. So the thermostat connects the control voltage at R to Y and to G to control the unit operation. So that would be in a call for cooling. Too many interruptions. I apologize. I am never not busy around here, but I'm gonna turn this off. And I don't know if I'm gonna make that 10 meeting in 10 minutes because I'm trying to get in the zone here. So, all right. So we know R is what? Our 24-volt supply. So that's where we start. We know Y is our what? That is our cooling circuit. This we know. So we send we send 24 to Y and to G on a call for cooling. Y is energized anytime there is a call for cooling. Thermostat terminal G, indoor fan, in auto position. G is energized also in a call for cooling, but if you switch it to on, obviously the fan's gonna run constantly. Then we move down to the next part of the sequence. So evaporator drain float switch is what they're calling it. We call it a flood switch or a flood safety switch. That's the one that we always put in our secondary in the evap coil. So that breaks Y. I know some of you had a chance to wire it up. Some of you may not have had a chance, but there's gonna be two legs. One goes to the Y terminal at the board, the other one wire nuts to the actual Y wire coming from the thermostat, and also the second Y wire that's going out to the condenser or to the contactor out at the condenser, which would be your signal wire. That's how you connect your flood switch. And then the other end, and so yeah, one goes to the board, one goes to the actual Y. And then over here, the indoor fan relay closes contacts when the coil is energized. So the indoor fan G is still operating, even if the Y is broken by the flood switch. G is still energized because if it's on. Well, yeah, even if it's on auto, G is still energized because the board is still sending the signal for cooling, but the condenser is actually going to turn off because the flood switch. So then moving on, we have the low pressure switch and a high pressure switch. So those two will be wired in series. And on the systems we have in class, we only have the high pressure switch. And as you can see, it's that yellow wire that goes into the pressure switch and then out of the pressure switch and then to the contactor coil. And then the other side of the contactor, and then connects to the Y, and then the other side connects to common. So those yellow wires that we have in class, that's connected to your high pressure switch. Systems that have high and low pressure switches are wired in series. So if it shuts off on high head or low head pressure, either one will cut the compressor off so we don't damage the compressor in either a high pressure situation or a low pressure situation. So those two would be wired in series. And the low pressure switch is first in this sequence, high pressure switch is after that. Then the anti-short cycle timer or the time delay will be next in that series. And then once we confirm that this switch is closed and this switch is closed and this switch is closed, then we're gonna energize the timer. And then after that time delay, it's gonna go ahead and energize our compressor contactor. Closes contacts when the coil is energized. So that 24 volts that went from R is shot down to Y, and it had to go through our flood switch and our low pressure switch and our high pressure switch and our time delay relay, and now to our compressor contactor coil, pulling it in and finally giving us our AC. And then down here is the run capacitor, which is next. Required for the condenser fan to operate. Frequently, pretty much almost all the time, the condenser fan and the compressor run on a dual capacitor rather than two separate run capacitors. Run capacitor required for fan operation. But yeah, so most split systems, you're gonna have a dual capacitor out at the condenser. Start capacitor required by some compressors to start, and then potential relay required if compressor has a start capacitor. So that is the sequence of operation for this particular chart. That is a sequence that I feel like y'all are pretty familiar with. And we're just gonna keep talking about it until y'all done. Some of y'all are done this mod too. Congrats for that. All right, moving on. Preliminary system inspection. Is the thermostat or system control set accurately? Sometimes it's a user error that's making the whole system not work correctly because they don't know how to use the thermostat. Next is the air filter clean? We talk about that all the time. It's a common occurrence that people freak out, don't know why their system's not working, but they have never changed their filter since they moved into that home years ago. Is there enough airflow or water flow? Dirty filter mess up that water flow or airflow, or other factors can mess up the airflow. Dirty condenser coil or poor water flow on a water cooled system would, is also something that would prevent the system from operating correctly. Is the system operating voltage within nameplate rating? So you got basically, are you short? Are you low on voltage? I've had that happen before. You always want to start at the source, open up that disconnect and check and make sure you have the correct voltage. You don't want too little because it's not going to run. You don't want too much or you'll burn something up. Is the system control voltage correct? So that's when you have to check your secondary side on your transformer. If you got 120 coming in, but you don't have 24 coming out, then you know you got a bad transformer. Collecting operational data. Operational data consists of system performance tests, homeowner information, diagnostic codes. So collect data that tells, let's start with the homeowner. So homeowner, verify information from homeowners as statements may not always be accurate. Information is typically general, not specific. So you kind of got to pull as much out of them as you can, and then, and just kind of take it with a grain of salt and then go see for yourself. Diagnostic codes. Diagnostics consist of LEDs that flash a 1 or 2-digit code. Codes are listed in the manufacturer's service literature on the unit system performance tests. Oh, sorry, I'm mixing stuff together. So y'all real familiar with that by now. Those diagnostic codes coming up, and you check the panel. It breaks it all down on the data tag, all what each code means, and you can't get like totally locked into those codes because they don't tell you everything, but they're a very good guideline. And then also, if the codes are making absolutely no sense, we know by trial and error it's probably a bad board. But you want to confirm that with your voltage test, which we've done. So system performance tests. Let's move that down. Provides more detailed information on the system, checking for refrigerant pressure, superheat, subcooling, temperature change, electrical current draw. Purpose is to allow comparison between actual performance and factory specified performance. So yeah, you want to compare your data to the data tag and see where you stand. If your amps are supposed to be 20, you're coming in at 25, you're overamping, or if your data tag says your target subcool is 8 and you're coming in at 3, then yeah, you're low. Recognizing incorrect operation. Troubleshooting begins here. Experienced technicians will quickly recognize incorrect operation in familiar systems. Compare factory specs to actual operation. This is considered the most accurate way to recognize incorrect operation. Testing to isolate the cause. Proceed from general to specific. Understand what the system should do, determine what the system is doing, determine what the system is doing incorrectly. Now move on to general investigation. Testing to isolate the cause. The process of elimination. Follow a logical pattern of investigation. Have a purpose for each test performed. Each test should be or should help narrow the focus. Logical electrical troubleshooting. This is the good part. So line voltage to the unit. Overload devices can open due to power interruptions. So make sure that, basically your breaker might be blown. Check, make sure that's not the case. Make sure you have your power coming from the source. Check system operation after replacing a fuse or resetting a breaker. You want to see if there's a condition that's going to make that occur again. Check all major loads, main power wire connections, and check amp draw control. And check amp draw. We all know high amp draw, bad motor. You want to check the cause. There could be something causing that motor to pull more amps, but at the same time, the stress of running at that high amperage for however long is going to degrade the motor. Control voltage. Transformer may have no line voltage. So if you don't have control voltage, back it up and see, do you have your primary voltage? If you do have your primary and there's nothing coming out of secondary, it's the transformer. If you don't even have voltage at the primary, then now you got to take it a step further and go step further back in the process. Or if you had started from the source to begin with, then you would already know. So voltage to non-functional components. Determine if problem is in the component or the circuit to the component. In other words, if the motor's not turning, determine whether or not it's a bad motor or if it's the circuit to the motor, aka is there power to this motor? If there's no power to it, then that's why it's not turning. If there is power to it and it's not turning, you got a bad motor on your hands. Moving on. Sorry, y'all. I keep getting little visitors at the window. Circuit to non-functional components. Locate the break in the circuit, and then in hopscotching, which is how you'll locate the break. Hopscotching is you pull that meter out. You put one on your neutral, put your other one on your line voltage, and then you see if you have power there, and then you just go from one point to the next in the sequence until you get to the point where you're losing power. That is hopscotching. Logical electrical troubleshooting continued. Circuit to the component that is not functioning. If non-functional component has no voltage, check the circuit to the component. Hopscotching. Start at one point where there is correct voltage and move one lead at a time from point to point in the circuit toward the functional load until the voltage is lost, and then you will have you'll find your problem. Refrigeration cycle troubleshooting. So these are the things you want to check for that. Low side pressure, high side pressure, suction line temperature, discharge line temperature, liquid line temperature, air or water temperature rise across the condenser, air or water temperature drop across the evaporator. The first thing to check with any refrigeration problem is the flow across the evaporator and condenser. Once proper flow is established, system operating data can be collected. Clean the coil before if you're diagnosing the system, your pressures look all crazy. Before you start adjusting anything, take a look at the coil. If you got a toe up, dirty, nasty coil, that's going to throw your pressures way off. Or of course, if there's no airflow across that coil, meaning either again dirty or blocked by something, or if the fan ain't turning. We talked about the 3 mass fluid flows. The refrigerant flow is one of them, and the other 2 are airflow. Airflow across the coil, the evap coil, airflow across the condenser coil. So if those ain't right, it's going to throw your pressures way off. So correct that. Make sure that's right. Make sure, at least you just look at the filter and look at the condenser coil and make sure the fans are turning before you start making judgment calls on the refrigerant. So moving on. Suction line superheat, liquid line subcooling, condenser temperature difference, or evaporator temperature difference. The 4 most important indicators require a comparison of data. Suction line superheat is the difference between the actual suction line temperature and the refrigerant saturation temperature. Saturation temperature is obtained from the suction pressure using a refrigerant pressure temperature chart. Liquid line subcooling is the difference between the saturation temperature obtained from the discharge pressure using the pressure temperature chart and the actual liquid line temperature. So I'm pretty sure y'all know what I'm about to say next. Your digital gauges will tell you your saturation temperatures automatically. It'll calculate your superheat and subcool automatically without having to whip out a pressure temperature chart. Definitely want to keep a pressure temperature chart handy. Be familiar with them and how they work, especially if an employer asks you any questions about it. Don't want to look dumb, but get your field piece digital manifold gauges for Christmas, and you won't have to do all the extra to try to calculate your superheat and subcool. Recommended corrective action. The technician's job is to solve problems. The customer should be offered at least one solution. Corrective action is sometimes obvious. Solve the problem, not the symptoms. That's the time to shine right there. This is the money part. It says corrective action sometimes, no, not that part. The customer should be offered at least one solution. Break it down for them. A lot of people tend to appreciate when you prioritize it. Like, okay, you have 3 problems, 2 are critical, 1 can wait. A lot of people they just, it kind of makes them feel like you're not trying to gouge them, or you're not, just trying to upsell them. So I tend to do that where I can. But basically, this is the part where the money is made. So you break down the problem, educate them as best you can without confusing them. One of the compliments I get the most in the field is that, wow, nobody told me that before. Oh, I never understood it like that. So that's one of the things, that's my selling tool, educating the customer. I find a lot of people don't like to be fast talked and upsold, and I don't like to, so I don't do it to people. I try to do it with my technical knowledge. I try to break it down in a way that makes them feel like it's necessary, even if it's not an emergency. I try to explain the necessity, and it usually tends to work. So that's the part where the money is made. So in summary, technicians should view units as systems, keeping in mind the interrelationship between the electrical, refrigeration, and airflow system components. Troubleshooting can be broken down into the following steps: understanding system operational sequence, preliminary system inspection, collecting operational data, recognizing what is operating incorrectly, testing to isolate the cause, recommending corrective action. Excuse me. When troubleshooting the refrigeration cycle in a system, key performance indicators include the following: low side pressure, high side pressure, suction line pressure, suction line temperature, discharge line temperature, and liquid line temperature. Those are all the things that you're going to use to do your troubleshooting. So, after the electrical stuff, start off with the simple stuff, then you move into the more complicated stuff, and you will find your problem. And if you absolutely cannot figure it out, call tech support. And if they can't help you, then call me, and then I'm gonna call tech support. Now, so anyways, I hope y'all learned something from that. Again, use your book in combination with what we just covered, because it goes even deeper, actually a lot deeper. So definitely lean on your book, especially now when there's no class time and we can't really interact and ask a lot of questions. So read that book. And then also in the emails that I sent out, there's links to YouTube videos and stuff. So definitely check out the videos and try to stay submerged in the industry, so that when we come back, you don't feel like you're starting all over. Because with or without UEI, your career started already once y'all got here. So now it's up to y'all to just continue to stay, updated and just stay fully engaged in all things HVAC. So check out those videos. And also, there is Unit 92 review questions on Flexi Quiz. So get that done, and I will check in with y'all later.